So good morning / afternoon / whatever time it is, everyone. It's really nice to welcome you to our Supernova seminar series. And today we have Damiano Fiorillo here. Now, Damiano did his PhD at Naples, finished that in 2022, and he's now a postdoc at Niels Bohr Institute in Copenhagen. And he will tell us about supernova neutrinos as a fluid and about neutrinos' secret interactions. And I look forward to hearing about those secrets. So,
Okay.
Damiano, please just go ahead.
Yes, thank you very much for the introduction, and thanks a lot for the invitation. So yeah, as Josh was saying, I will be talking about supernova neutrinos as a fluid, and in particular, the impact of novel interactions in the neutrino sector on supernova neutrinos. More broadly, I think the main topic I want to cover is what is the impact of new physics, specifically new physics related to the neutrino sector, on the phenomenology of supernova neutrinos. And so as a brief outline of what I will be talking about, I will start with briefly reviewing a few basic topics that we need for the rest of the talk about supernova neutrino emission in general, and a very brief review of the observations from supernova 1987A, because some of this will be relevant for the later part of the talk, and in particular the neutrino observations from supernova 1987A. And afterwards, I will pass to the core part of the talk, where again, the question I want to tackle is really how can neutrinos probe new physics in the neutrino sector? And I will divide the discussion into two separate parts. The first one relates to novel particles that couple to the neutrino sector with a weak coupling. So these novel particles can be emitted from the core of the supernova and escape, and they produce a certain kind of phenomenology that I will discuss. So I will discuss a new way of constraining these emission from new particles from supernova. And later I will pass to the main part of the talk, really, which is what happens instead in the case in which you have new particles coupling to the neutrinos so strongly that they do not actually leave the supernova core, but they actually act as the mediator of a new interaction in the neutrino sector alone, which for various reasons are called secret interactions. So this is really the part where the neutrino fluid actually, which was in the title, enters the game, because when secret interactions are so strong in the neutrino sector, then neutrinos do not behave as individual particles, but they interact strongly and behave as a collective fluid. So this will be the main part of the talk. And so starting with the main topics that we will need about supernova neutrinos. So core collapse supernovae are the endpoint of the lifetime of very massive stars. At some point, the core of the star becomes dominated by iron nuclei, which are very stable and therefore cannot fuse any further. So in the absence of fusion, of nuclear fusion, there is a lack of pressure support, and the core of the stars starts to collapse. And in the collapse, the density of the matter becomes larger. It becomes so large that at some points, neutrinos, despite having only weak interactions, remain trapped by their interactions with the nuclear matter. And at some point, it becomes so large that it becomes comparable to the nuclear density, so the density of nuclei. At this point, the equation of state abruptly changes, and what happens then is that there is a rebound from the core, from the core at nuclear density. A shock wave is launched towards the outer mantle. And the shock wave is not able by itself to make it out of the star. But at the center of this, so at some point it stops, leaving at the center a proto-neutron star, so a very compact remnant at near nuclear densities. And this proto-neutron star accretes matter from below the shock wave. And at least in the neutrino delayed explosion mechanism, this accretion powers, which is the most commonly understood mechanism for powering the supernova explosion, this accretion of matter on the proto-neutron star powers neutrino emission. Neutrinos deposit a little part of their energy below the shock wave, but the little part of the energy that they are able to deposit is enough to revive the shock and make it finally explode out of the star. So this is what the real supernova explosion. And after the real explosion, which typically happens from 300 up to maybe 700, 800 milliseconds after the primary bounce, at this point, accretion stops, and it starts a new phase, which is a phase of cooling of the proto-neutron star, in which the proto-neutron star cools down of its excess energy by emitting neutrinos over a time scale that is of the order of seconds, so 5 up to 10 seconds perhaps. So these are the main features that really we will need for the rest of the talk about the nature, the process of core collapse supernova. Everything I will talk about relates mostly to this early cooling, accretion and cooling phase, and the neutrino emission in these two stages. So the other topic that I wanted to review before delving actually into the real new stuff is the neutrino observations from supernova 1987A. The supernova 1987A was a supernova explosion, probably one of the most well-known supernovae because it exploded close enough to the Earth. It was in the Large Magellanic Cloud, so 150 kiloparsec away from Earth. And it exploded close enough to the Earth that we were able to detect a burst of neutrinos coming from the supernova. And this has been the first and last time in history in which this has been possible. And so the main channel for the detection of neutrinos from supernova 1987A was inverse beta decay. So it was the collision of anti-electron neutrino with the protons in water Cherenkov detectors. In the collision, a positron is produced, and the positron leaves an electromagnetic signature, in particular Cherenkov radiation. So we can directly measure the passage of a neutrino by looking at the Cherenkov radiation from the positron. One thing I want to emphasize about this inverse beta decay process, because it will be relevant for later, is that the cross-section for inverse beta decay increases as the square of the neutrino energy approximately. This will be relevant for later. This really means that high-energy neutrinos are more efficiently detected inside our detectors because they have a higher cross-section for interacting inside the experiment. And so the picture that supernova 1987A gave us about supernova physics mostly come from these two experiments, Irving Michigan Brookhaven detector, the IMB detector, and the Kamiokande detector. So one was in the US, one was in Japan. Both of them were water Cherenkov detectors. So they were big tanks of water detecting the Cherenkov light from this inverse beta decay reaction. They both detected a burst of neutrino events. They had somewhat different characteristics. IMB was somewhat more sensitive to higher energy events. Kamiokande was more sensitive in the low energy part of the spectrum. But what I want to stress really is that these events provide a picture that sometimes has been claimed to be in tension between one another, but the tension is not strong. More or less, they provide a generally consistent picture, both between one another and with the up-to-date simulation. So we have recently reanalyzed the data in light of up-to-date simulations, one-dimensional simulations, and we have found that they provide a generally consistent picture, both for the energetics and the average energy of the signal. So overall, I would say these observations have confirmed what we more or less understand about the supernova mechanism. And so with these premises, I can now pass to the main part of the talk, which is really how new physics in the neutrino sector is able to impact the phenomenology of supernova. And I will start with supernova 1987A. And as I mentioned, I will start with new particles that couple to the neutrino sector with a relatively weak coupling. So these new particles, even if the coupling is relatively weak, we're talking about 10 to the minus 6, 10 to the minus 7, or even lower. With these couplings, these new particles can be produced in a supernova core. For the typical density and temperature conditions, even particles with a mass of up to tens or 100 MeV can be produced with these couplings. So the challenge is not so much to understand that these particles can be produced, but rather to understand what observables could be affected by the emission of novel particles from the core. This is the real challenge of setting bounds using on new physics using supernova observations. And for a long time, historically, the main observable that has been used for this purpose is the duration of the neutrino burst. So the idea was simply stated that if the proto-neutron star is able to emit new particles, then it is able to cool faster because it has an additional channel for energy cooling beside the standard one. And if it cools faster, since its energy budget is the same, necessarily the duration over the typical time over which it cools must be shorter. So we expect a shorter burst if the proto-neutron star is able to cool in a non-standard way. So this led to these energy loss bounds or cooling bounds, which were based on some simulations from the 90s, which showed that if the luminosity in the new particle, which here I am denoting by phi, we can think of it as a new boson coupling to the neutrino sector. If the luminosity in the new boson becomes comparable with the standard neutrino luminosity, then we can expect a significant shortening of the neutrino burst, and therefore we can exclude this possibility because supernova 1987A provided the duration of the burst comparable to the one that we expect. So these cooling bounds, one thing I want to stress about these cooling bounds is that they necessarily rely on a feedback on supernova physics because they rely on the emission of the new particle influencing the physics of the supernova by definition. So the main point of this part of the talk is that we have now provided a new criterion for constraining novel particles coupling to neutrinos, which can provide stronger bounds and at the same time does not rely on any feedback on the supernova physics. The idea of these novel bounds is actually relatively simple. In the standard picture, neutrinos are emitted mainly from the surface of the protoneutron star, where they run out of equilibrium with matter, and therefore they are emitted in a quasi-thermal way, let's say. The typical energy at the surface of the protoneutron star is of the order of tenths of MeV. At most, maybe it reaches 40, 50 MeV. But that's the typical energy we must keep in mind. So standard supernova neutrinos are expected in this ballpark of energy. On the other hand, new bosons coupling to neutrinos would be produced in the very core of the protoneutron star. And in the core, the typical energy of neutrinos are much larger because neutrinos are degenerate and they have a typical average energy, which can be even 100 or even possibly even 200 MeV, so much larger than the one of the neutrinos that we observe at Earth. So these bosons are produced in the core with this very large energy, and then they escape the supernova freely. And then at some point on their way to Earth, they will be able to decay back to neutrinos, and they will produce a secondary source of neutrinos, which are high energy compared to the standard ones, because are expected to be in the 100 MeV range. So there is a clear separation of scale between the standard supernova neutrinos emitted from the supernova mechanism and the non-standard high-energy neutrinos produced by these new bosons decaying outside of the supernova. There is also reason to expect that the non-observation of high-energy neutrinos from supernova 1987A can set constraints which can be more stringent than the cooling bounds. And the reason goes back to something that I anticipated a few slides before, which is that the cross-section for inverse beta decay of high-energy neutrinos is larger for these high-energy neutrinos. They interact more efficiently inside our detector, and therefore they should produce more event than the standard supernova neutrinos if they have the same luminosity. So indeed, by a simple order of magnitude estimate, if we look at the ratio between the number of events from the non-standard neutrinos and the number of events from standard neutrinos, this is proportional to the ratio of the cross sections. And because the ratio of the cross section can be as large as a factor 100, we find that this ratio number of events is 10 times larger than the ratio of the luminosity. So if you saturate the cooling bound, if you have a supernova emitting just as much energy neutrinos as it emits in the new boson, you expect 100 events inside your detector from these high energy neutrinos, and you have observed none. So even this very simple order of magnitude estimate by itself is able to tell us that this new observable is more powerful than the cooling bound. In order to make this estimate more quantitative, we have to fix a specific model of new physics. We do so by choosing a new particle that coupled with a Majoron-like coupling. So it's this boson coupling to pairs of neutrinos or pairs of antineutrinos. So this new particle is dominantly produced inside the supernova by the coalescence of pairs of neutrinos or of pairs of antineutrinos. And then it leaves the supernova and it decays outside. By computing the emissivity inside the core and comparing with the data from IMB and Kamiokande, which did not observe any event above 50 MeV, we were able to obtain these bounds in the parameter space, which are now introduced. So this is the mass of the particle, the mass of the Majoron or new particle coupling to neutrinos versus the coupling of the particle. And these blue lines correspond to the new bound that we have obtained. You see that there are two lines because we have tested the two different supernova models, one which had a particularly light protoneutron star and one that had a particularly heavy protoneutron star. So this is expected to bracket the reasonable case for supernova 1987. And you can compare these bounds with the green line here, which corresponds instead to the energy loss bounds based on the cooling criterion that I mentioned a few slides ago. You can see that the new bounds are an order of magnitude stronger than the energy loss criterion, an order of magnitude stronger in coupling. Now, typically, emissivity is proportional to the square of the coupling. So that means we are really constraining the luminosity of the new particles to be smaller than 100 times smaller than the neutrino luminosity. So these are significantly stronger bounds. So in order to connect to the next part of the talk, let me mention here that there is a dashed line in this region. So this dashed line is the starting of what is typically called the trapping regime. For larger coupling, the decay lifetime of the new particle is so short that the particle decays before leaving the protoneutron star. So it is not able to freely stream out of the protoneutron star as we have assumed for these bounds. What happens out above this dashed line is therefore very difficult to predict because there is a definite feedback on supernova physics. So we cannot predict simply what happens in this trapping regime. And that's exactly now what I want to talk about next. So what happens when we take the opposite limit of very large couplings, so say 10 to the minus 3, 10 to the minus 4? How does the phenomenology change? So this is the next part of the talk. And I really want to focus on coupling so large that, as I mentioned in the beginning of this talk, the new particle, the new boson, is not able to escape, and actually is not able to even exist as a real particle. It rather exists as a virtual mediator of a new interaction in the neutrino sector, which is often called a secret interaction. So this topic of secret interaction is a topic that has recently gained a lot of attention for a variety of reasons. This is the typical parameter space that people have in mind when they think about secret interaction. This plot comes from a SNEWS report, which was entirely devoted to the topic of secret interactions. So this is the coupling of the mediator to the neutrino sector, and this is the mass of the mediator. One thing I want to emphasize is that for the rest of the talk, I will discuss a case of a coupling of a new boson that is lepton number conserving. So I switch compared to what I discussed a moment ago, which was lepton number violating. I will discuss lepton number conserving secret interactions. If you have questions about lepton number violating secret interactions, we can discuss later. But for the rest of the talk, I really want to talk about lepton number conserving secret interactions, which have an entirely different phenomenology. So as I was mentioning, this is the parameter space that people have in mind. And just to guide the eye, for masses of the mediator below 1 MeV, there are very stringent constraints coming from cosmology, especially from big bang nucleosynthesis. On the other hand, above 1 MeV, constraints coming from cosmology are mainly driven by the cosmic microwave background observations at relatively large couplings. And there is part of the parameter space, I should mention that some of these constraints depend a lot on the flavor structure of the coupling. But there is a part of this parameter space that is very difficult to constrain. And probably this is one of the reasons why these secret interactions have gained such a lot of attention recently, because it's a very challenging topic. And that's why actually they are called secret, because since they are restricted to the neutrino sector alone, it's very difficult to find environments in which there would be a strong impact. So one exciting challenge that has appeared recently, for example, is the observation of a diffuse neutrino flux of astrophysical origin from ice cube, which could be distorted by the secret interactions. And a lot of people were driven to these questions by these new observations. There are also other reasons why these secret interactions have become of interest recently. For example, people have realized that secret interactions could possibly relieve some tension between sterile neutrino candidates for dark matter in the KV region with the X-ray observations. But regardless of the motivation, the broad question I want to ask is, would the phenomenology of supernova be affected by secret interactions? It sounds like a reasonable question, because in today's universe, the core of the supernova is one of the environments in which we have the densest population of neutrinos. And in fact, the simple order of magnitude estimate shows that if we are at coupling like 10 to the minus 3 or even 10 to the minus 1, secret interactions are definitely quite active in supernova, because they are even stronger than the weak interactions. So they definitely are active in the core of the supernova. But just as in the previous part of the talk, the challenge is not to say that they are active, but it's rather to ask ourselves, is there some observable that could be affected or distorted by the presence of this secret interaction? So this is the question that will guide the rest of the talk. And it's the question that various people have tried to answer in the course of time. So I prepared a kind of a timeline of claims by different people of how people have tried to address this topic. So actually, the first person to address this question was already in 1987, immediately after supernova 1987 exploded. So this was Manoir. And Manoir proposed that if there are secret interactions, then the neutrinos would reach the Earth delayed compared to the standard scenario. The argument of Manoir was the following. He argued that in the standard case, neutrinos, in order to traverse a distance r, they simply move in straight lines. So they take a typical time r. On the other hand, because of the secret interactions, Manoir argues that the neutrinos actually move more similarly to a random walk, because they scatter with one another, and every time they scatter, they randomize their direction. So this lambda nu is the mean free path for neutrino-neutrino interaction. So every time they scatter, they randomize their direction, and therefore the time that it takes to traverse a certain distance r is not proportional to r, but it's actually r squared over the mean free path in a typical random walk fashion. And this can be much, much larger than the standard scenario, because it is enhanced by this ratio, radius over mean free path. I want to emphasize the appearance of this ratio, radius or distance over mean free path, because most bounds that we will discuss in the following are based on the appearance of this ratio, which can be as large as you want. Because if you increase the coupling, between the coupling of the new interaction, you reduce the mean free path for neutrino-neutrino interaction, and this ratio becomes larger. So you can make any observable become as large as you want if they are sensitive to this large ratio. I stress this because it will be our main point in our papers and in this talk, that actually no observable in supernova is strongly sensitive to this large ratio radius over mean free path. So this will be an important, let's say, a main character for the rest of the talk. So Manor concludes that since we have not observed a delay in the burst of the neutrinos in 1987, we can constrain the new interaction. And the mistake in Manor's argument was quickly identified by Dijkus and collaborators. So they noted that if the mean free path is so small, well, first of all, they noted that in each individual collision, it is true that the direction of an individual neutrino gets randomized, but on the other end, the total momentum of the pairs of colliding neutrinos is conserved. So it is not possible that we have such a delay because the total center of mass velocity of all of the neutrinos together is conserved by the neutrino-neutrino collisions. So Dijkus and collaborators noted that if you have a mean free path that is much shorter than every other characteristic distance, it doesn't make sense to think about individual neutrinos in the kinetic sense. We should rather think about the total neutrino collection as a fluid, because the secret interaction maintain it as a fluid, strongly coupled throughout all the dynamics. So the bounds proposed by Manor were quickly discarded. But now flash forward by 20 years, and people are again asking themselves whether the phenomenology of a supernova could be affected by secret interactions, because as I mentioned, there are new motivations for looking at this problem. So one other possibility was proposed in 2019, where people proposed that if there are neutrino secret interactions, there should also be number changing neutrino secret interactions, in which pairs of neutrinos produce two pairs of neutrinos in the final state. So the number of neutrinos changes, which means that also the average energy of the individual neutrino changes, because now we have twice the particle, and because of energy conservation, the typical energy of each individual neutrino must go down by a factor 2. Now, if we have many such collisions, we can expect that the average neutrino energy goes down by a factor 2 to the power of the number of collisions. But the number of collisions is exactly the large ratio that I mentioned a moment ago, is the distance traversed over the mean free path. So the conclusion of this paper was that we should expect a dramatic reduction in the average neutrino energy because we have an observable that is exponentially sensitive to the large ratio distance over mean free path. So the last step in this timeline is a paper from 2022, in which the authors are posing the very interesting question of how would neutrinos be emitted from the core of a supernova if they are a fluid? This is really the central question, so it's a very interesting one, and the authors do not provide a conclusive answer to the question, but they do envision two scenarios, and they believe that one of the two scenarios does obtain in supernova. So one of the two scenarios they call the wind outflow. It's a scenario they decided not to focus too much for this paper, and so it's the discussion that I will provide mostly comes from an appendix. So this wind outflow is a steady outflow of neutrinos from a stationary protoneutron star, which emits in stationary rate. And so obviously this scenario cannot be a complete answer to the question, because by definition supernova is a transient. The phase in which the protoneutron star cools down only lasts for a finite amount of time, some seconds. So this wind outflow, in our dynamical treatment, we do find that there are some steady features which this wind outflow correctly captures, but these features mostly relate to the region close to the protoneutron star and only during the cooling phase. After the protoneutron star cools down and very far from the protoneutron star, the emission is, of course, has dynamical features which cannot be captured by this wind outflow solution. So the other scenario that the authors focus on is instead a dynamical scenario, which they call the burst outflow. The picture that they have in mind for this scenario is a ball of neutrino fluid, which is initially left free to expand in vacuum. This condition does not have much to do with a realistic supernova condition, but it's still an interesting condition because it looks like a very generic mechanism of injecting energy in the form of a relativistic fluid. So it's an interesting question to ask, how would such a free expansion proceed? And the authors claim that if you leave this ball of neutrino fluid at rest and you leave it free to expand, it evolves into something that keeps expanding while maintaining homogeneity. So I want to stress the homogeneity because it's really the key word of this burst outflow. They claim that the ball remains homogeneous all the time while its radius expands, which, remember, the radius is really what sets the duration of the burst that we see at Earth, because in the end, what we observe at Earth is the entirety of the ball. So if the radius goes up, this means that also the duration of the neutrino burst increases compared to the standard case. So the authors conclude that the typical duration of the supernova neutrino burst should be increased by a power of the large ratio radius over mean free path, which appears again. So I think this picture of a homogeneous expansion makes intuitive sense when we think about non-relativistic fluids, because non-relativistic fluids have a tendency to smoothen inhomogeneities. So if we set up an inhomogeneous density profile for a non-relativistic fluid, the non-relativistic fluid will quickly fill any underdense region and tend towards homogeneity. However, for relativistic fluid, this is actually not the case, as I will show later. So the numerical simulations that seem to support this claim, which were not published by the paper, seems to be in conflict with previous literature. So I will return to this topic later after I show our own simulations on the topic. Instead, now I want to discuss how we do tackle the problem. And the way we tackle the problem is really to look at all different stages of neutrino emissions. So that means starting from what happens inside the protoneutron star, which is a phase that previous authors have somewhat underestimated. But even inside the protoneutron star, actually, neutrinos are, even in the standard picture, are one of the main agents of energy transfer between one part and the other of the protoneutron star. So it makes sense to ask, if neutrinos are a fluid, does heat transport in the protoneutron star change because of their fluid nature? And later I will discuss the stage of emission from the protoneutron star surface. And after the protoneutron star cools down, the neutrinos leave the protoneutron star and start to evolve as a fireball. I will define what a fireball is later, but for now we can just think of it as a shell of neutrino fluid freely expanding without any interaction with anything else. So it's just freely expanding in vacuum. And then finally, after some time, the density in the neutrino fireball will go down by so much that the secret interactions will decouple, in the sense that they will become too slow because the density is low. And so the neutrinos start to behave as in the standard case, so that the secret interactions will decouple. So I will discuss each of these different stages in turn. And I will start with what happens inside the protoneutron star. So the heat transport inside the protoneutron star, how is it affected by the secret interaction? Now, in the standard scenario, neutrinos behave as individual particles, and they typically propagate from regions of high temperature to regions of low temperature, driven by a kind of random walk dynamics, because they scatter between nucleons with a typical mean free path lambda nu n. Please notice this is not the same lambda nu that I introduced above. This is the mean free path for neutrino-nucleon interaction, so it is a completely standard quantity. Of course, this is a special type of random walk because neutrinos are also absorbed and then re-emitted by the nucleons, but still the dynamics is diffusive. And so the heat flux between one point and the other of the supernova of the protoneutron star must be proportional to the neutrino-nucleon mean free path, because the larger the mean free path, the longer is the distance that neutrinos can traverse transporting energy. And by dimensional analysis, it must only be completed by the gradient of temperature, or actually the gradient of the energy density. So this estimate is well known from kinetic theory, and it's the typical heat flux estimate for a certain temperature gradient. How does this picture change in the case of strong neutrino secret interactions? Now, in this case, it doesn't make sense to think about individual neutrinos or Boltzmann equation or other concepts from kinetic physics, because individual neutrinos lose their property pretty quickly by scattering with all the other ones. We really should think about the fluid. And fluids, as we know, have a tendency to go from region of high pressure to region of low pressure. Specifically, this happens because the pressure gradient gives momentum to the fluid. Inside the protoneutron star, this momentum must be, so the pressure gradient must be balanced with the momentum that the neutrinos lose via neutrino-nucleon scattering. So we must balance this pressure gradient with the momentum loss to the neutrino-nucleon interaction. By doing this balance, one quickly realizes that the heat flux is again proportional to the neutrino-nucleon mean free path times the pressure gradient. And because for a relativistic fluid, pressure is directly proportional to the energy density, this turns out to be exactly identical to the standard case. So even though the physics is quite different, because now it's a pressure gradient driving the motion, not a temperature gradient, we still have the same conclusion. The heat flux is proportional to the temperature gradient. Now this, of course, for the slides, I reserved only a very simplified version of the calculation based on dimensional analysis, but in the paper we provide a full calculation and we show that even the numerical coefficients are actually identical. So really the heat transport, somewhat surprisingly, is not strongly affected by neutrino secret interactions. We have shown that there are some caveats to this conclusion. So for example, if the neutrino-nucleon mean free path strongly depends on energy, which we know it's actually the case, then there can be order unity changes in the numerical coefficients for the heat flux. But these changes are, again, factors of order unity. The large ratio distance of a mean free path is not appearing anywhere. So we do not expect large changes in the phase of heat transport inside the protoneutron star. So now maybe the main stage I want to discuss actually is what happens when the neutrino fluid is emitted from the protoneutron star towards the outside. It's the most complicated phase because inside the protoneutron star, the dynamics of neutrinos is diffusive, whereas outside the protoneutron star, the dynamics of neutrinos is purely fluid because they are not interacting with anything else. So it's the most complicated phase to capture. And in a very idealized first approximation, we can think of these as a spherical black body radiating into a vacuum. The protoneutron star, in a sense, is similar to this. It's a sphere. Of course, the temperature is not exactly constant, but this is a very qualitative first grasp at the problem. It behaves as a sphere radiating into a vacuum. So this will be the toy problem that we will analyze. But before looking at the sphere radiating into a vacuum, which by itself is still a pretty complex problem because it is a dynamical problem, the sphere keeps emitting into the vacuum for a long time. So as a preliminary exercise, we have looked at an even more simplified problem, which is a stationary problem, in which we have two bodies, one at the temperature T1 and one at the temperature T2. So one is hot and one is cold. And the neutrino fluid, and in stationary condition, a neutrino outflow is established from the hot to cold body, transferring energy from the hot to the cold body. We want to investigate what are the properties of this outflow. This is a very idealized problem that has nothing to do with the real supernova, but we can imagine that emission into a vacuum is similar to the limit of this problem when the temperature of the cold body goes to zero. Radiating into a vacuum is similar to radiating into a zero temperature environment. So this is why we are looking at this idealized problem to start with. I'm also introducing here some notation. This B here is the black body energy density. So we can think about this as simply the fourth power of the temperature of the body, because that is the typical black body energy density for relativistic particles. Okay, so the way we tackle the problem is by solving the steady fluid equations, assuming that inside each of the body, the neutrino fluid is thermalizing with the typical temperature of the body, whereas in between the two bodies, it's simply left free to move without any other interaction. And these are the typical outflow, the typical flow property that we obtain. So this is as a function of space. The pink and the cyan region are the hot and the cold body respectively. And this is the bulk velocity of the flow and the energy density of the flow. So let's first look at the red curve. The red curve corresponds to the case where the cold body has a temperature that is not too different from the hot body. So in this case, because the difference in temperature is relatively small, the velocity with which the neutrinos flow between the two bodies is not too large because there is a small temperature gradient. And we find that the outflow is subsonic. So the velocity with which they escape is relatively small. Now, as we increase the temperature difference, so as we make the cold body colder, the outflow velocity keeps increasing until it reaches a point where it becomes sonic. So it becomes exactly equal to the speed of sound. What happens at this point is that even if we keep making the cold body colder, the outflow velocity can never become larger than the speed of sound. This is something that we have proven directly from the equations, that the maximum outflow velocity is sonic for emission from the hot body into a cold environment. So what do we gather from this idealized problem? The first message that we gather is that radiation into a very cold body, such as the vacuum, is expected to happen with the speed of sound. We will see that our dynamical picture does recover exactly this feature that we can get more simply from this idealized toy problem. There is a second property that we can gather from this idealized problem. And this is more easily shown by this figure. So this figure contains, as a function of the ratio of the temperature, this is actually the ratio of the black body energy density, but as I mentioned, this is directly proportional. This is the fourth power of the ratio of the temperature. So 1 corresponds to the two bodies having the same temperature, and 0 corresponds to the cold body being at 0 temperature. And the green line is the energy flux escaping, emitted from the hot body. So it's the rate by which the hot body is losing energy. And the solid line is for the standard case without secret interaction, while the dashed line is for the fluid case with secret interaction. What I want to stress is that if we go to the limit of B2, which goes to 0, so the limit of radiation into a vacuum or radiation into a 0 temperature environment, the outflow, the energy outflow, is essentially identical or very, very close for the two cases. So the energy flux that is emitted from a hot body into a very cold environment is nearly identical in a standard and non-standard case. Because the energy flux is the rate with which a body cools down, this means that the cooling time of the proto-neutron star is expected to be the same in the standard and non-standard case, which is a very non-trivial, I think, conclusion, but it's what we find by this idealized problem, that the cooling time of the proto-neutron star is expected to be identical or very similar between the standard and non-standard case, because the rate of energy outflow is identical in the two cases. So we can now look at the dynamical problem. Again, the dynamical problem I am referring to is a sphere radiating into a vacuum. So a sphere with, we can take as a first approximation an isothermal sphere radiating into a vacuum. We cannot now go with analytical solutions because this is a dynamical problem. It depends both on space and time. So we have to solve the full fluid equations numerically, assuming that inside the proto-neutron star, the neutrino fluid is in thermal equilibrium with the body via neutrino-nucleon interaction, while outside it is left free to propagate without any further interaction. And these are the main features that we observe. So this is as a function of space, the different curves correspond to different snapshots in time. This is as a function of space, the energy density. This is actually the energy density times the square of the radius, for a reason that will be apparent in a moment. And this is instead the bulk velocity of the outflow. So what we see is in this in this small region here for radius which are small, the fluid is in thermal equilibrium with the black body, so it doesn't change with time. But outside instead, we can see the front of the emission, which propagates with the speed of light. So it keeps going to the right with the speed of light, while in between it quickly settles into a nearly steady emission, where the profile of the energy density decreases as 1 over r squared. The r to the minus 2 dependence comes simply from energy conservation, so it can be proven directly by requiring energy conservation. And if we look at the velocity profile, we can see that also the velocity profile quickly settles into a stationary one. The main feature I want to emphasize about this velocity profile is that already very close to the proto-neutron star, the bulk velocity of the neutrino fluid is very similar to the speed of light. So even though at the surface, the velocity is the speed of sound, as we had already guessed from our previous toy problem, already at a distance of 60 or 80 kilometers, the velocity has become essentially the speed, very, very close to the speed of light. So the steady features can only go on for some time, and we know how much time. It is 5 seconds or 10 seconds, a typical cooling time of the proto-neutron star. In units of kilometers, 5 seconds correspond to something like 1 million kilometers. So we can expect that this phase of stationary emission goes on for a very long time. However, at some point, it will stop. At some point, the proto-neutron star will cool down so much that it will stop emitting. In this case, what we expect to happen is that the neutrino emission stops and it leaves a cavity behind it, because now the proto-neutron star is not emitting anymore. So the question that we now ask is, because there is a cavity, because there is an empty space between the neutrinos, are neutrinos dragged into the cavity by the lack of pressure? Because now behind the neutrino shell that I have drawn here, there is no pressure support. For a non-relativistic fluid, this would mean that the fluid would quickly fill the cavity and becomes homogeneous, as people had previously claimed. Is this true for a relativistic fluid? This is the question that we ask here. And in order to answer the question, what we do is we turn off manually the temperature of the proto-neutron star. So after some time, we explicitly put the temperature of the proto-neutron star at 0, and these are the simulations that we obtain. I want to stress something. Obviously, in a realistic supernova model, the cooling of the proto-neutron star is determined by the neutrino emission itself. So in a rigorous setting, we should have to account self-consistently for the cooling of the proto-neutron star because of the neutrino emission. But that would mean essentially simulating a supernova accounting for secret interaction. Because here we are interested in broad features and qualitative features, we do not do such a complicated and self-consistent problem, but rather we turn off manually the proto-neutron star and we look at what happens. And these are our solutions. You can actually see pretty clearly the moment where the proto-neutron star cools down, because there is this kink in the energy density profile, which corresponds exactly to the cavity that I have drawn schematically in the picture to the left. But what I want to stress about this solution is that there is a portion of the neutrino fluid that keeps moving with a speed very close to the speed of light and never feels that there is a pressure behind it. It is not able to, it is not driven to feel the underdense region because it is moving so fast that it is causally disconnected. In fact, this is a simple causality argument. The information that the protoneutron star has cooled down can only move with the speed of sound, but this part of the fluid was already moving for a long time with the speed of light. So the information simply cannot catch up. And this part of the neutrino fluid keeps expanding as if the protoneutron star had never cooled down. Now, from this simulation, it may look like this portion of the fluid is relatively small, but that's because of computational power. We had to turn off the protoneutron star down pretty soon. But in reality, remember that the steady emission goes on for a time of 5 seconds, which is, in these units is 10 to the 6 kilometers. So it's a huge energy scale. So really what I want to stress is that the bulk of the neutrino fluid keeps moving with the speed of light without ever perceiving that there is a lack of pressure support. And because it moves with the speed of light, the front and the end of this neutrino shell are moving with the same velocity. So the thickness of this neutrino shell cannot change. This is the main feature I want to stress, and it's the property of what is generally called a fireball solution. So a fireball are these typical solutions appearing in the expansion of relativistic fluids, not only neutrinos, but also gamma ray fluids, for example. And the main property of the fireball is that they are highly non-homogeneous because they are limited to this shell, which propagates and expands with a constant thickness. So another thing I want to stress here is that we do account in our simulations for number changing reactions of the form 2 to 4 reactions, yet we do not find any large change in the average neutrino energy. And the reason is that in reality, the inverse reaction always has a comparable rate with the direct reaction. So the previous estimate that I showed in the previous paper was neglecting the inverse reaction, but detailed balance shows that in every little volume element, because the distribution is very close to black body, the 2 to 4 and 4 to 2 reactions have very comparable rates. So in reality, there is no dramatic reduction in the average neutrino energy. Overall, our conclusion from this problem is that there is actually no observable that is affected by the large ratio distance over mean free path or protoneutron star radius over mean free path. No observable is affected by large factors. There are only order unity changes which are not able by themselves to be large. One other question I want to tackle is whether this fireball formation is a general outcome or whether it's actually driven by our conditions. Our conditions are motivated by supernova physics, so they are the most realistic one. Yet one can ask, well, for different conditions, is it possible that we find an evolution that is not similar to the fireball formation? So in order to settle this question, we have also looked at a different initial condition, not motivated by supernova. This is the initial conditions that, as I mentioned, was studied in the previous paper. So it's a ball of neutrino fluid initially at rest, a ball being in vacuum. And these are our simulation. This is again energy density times r squared as a function of radius. You can see that what happens is that the fluid escapes from the surface and it quickly settles into a shell of neutrino fluid that moves with the speed of light again. So we have the same feature even for a very different initial conditions. In fact, we can expect that this is a general outcome of the expansion of relativistic fluids when they are initially injected in a relatively small and localized region. In fact, I think it's an interesting point that we are in some sense rediscovering the properties of this fireball in the context of neutrino physics, because in reality, they are known in the other context of gamma rays or other relativistic particle expansion. So for example, they appear in heavy ion collisions. We have recently found that they can also appear in the case of heavy axions decaying outside of supernova. Probably the case in which they are best studied is the case of gamma ray burst, where we have in the fireball model of the gamma ray burst, we have a very similar problem. We have injection of a photon fluid in a very localized region, which at least in the early stages expands as a purely relativistic fluid. And in fact, this problem, this exact same problem that we have now looked at in the form of a neutrino problem, was studied already in the 70s by people in the gamma ray burst community trying to understand what was the free expansion of a relativistic plasma dominated by photons. The equational state is identical, so all properties are identical. And these people concluded exactly as us that the expansion essentially assumes the fireball formation with a shell of nearly constant thickness. So the thickness of the shell really does not change. This is a crucial property of this fireball formation. And I think from the point of view of pedagogical point of view, it's very interesting to compare what happens for a relativistic fluid and a non-relativistic fluid. For a relativistic fluid expansion, this is from a review of from a historical review of gamma ray burst by Fiorillo and collaborator, and we can clearly see the difference of the expansion of a relativistic fluid, where the fluid quickly settles into a shell of constant thickness that does not expand. It expands radially, but the thickness of the shell does not change. Compare this with a non-relativistic fluid, where instead homogeneity is always maintained and the density goes down while the radius goes up. So it's more similar to what had been previously claimed for the burst outflow, but it is a property only of non-relativistic fluids. So the final stage we look at is what happens after the density in the fireball has become so small that the secret interactions decouple, they become too slow. In this case, what we expect to happen is that the distribution function freezes in exactly the same value that it had before the coupling. And this distribution, as it always happens for a strongly thermalized fluid, is a black body, but it's a black body with a strong Lorentz boost because the fluid is moving with a bulk velocity that is very close to the speed of light. So at every point of the decoupling sphere, the distribution is a boosted black body. Now, when we at Earth look at different points of the sphere, we are going to see that when we look directly at the center of the sphere, because the neutrinos are moving collinearly with the bulk velocity, we are going to see a very hot black body distribution. Whereas if we look at the edge of the sphere, we are going to see a very cold black body distribution because we are looking at neutrinos at a large angle compared to the bulk velocity. Of course, we are not able to resolve spatially the different points of the decoupling sphere. So when we put it all together, we find a distribution that is not a black body because it is the convolution of all these different black body distributions. So it's not a black body, it's a different distribution. So there are differences in the spectrum that is expected at Earth because of the secret interactions. But when we look quantitatively at these differences, this is what we find for this idealized problem of a black body radiating into a vacuum. The black line is the standard black body case expected in the absence of secret interactions, whereas the blue and the red curve are what we expect in the presence of secret interactions. The different color correspond to the case in which we do account for number changing or we do not account for number changing reactions. You can see that the difference is very small. And the reason is that number changing reactions really only want to enforce chemical equilibrium, which already at the beginning is very close to being enforced. But really what I want to stress is that both of them, when compared to the black case, do not exhibit large changes. There are some changes, but they are order unity changes. So they are not dramatic differences. And so this really brings me to my conclusion. What I wanted to stress is that supernova even today remain an ideal laboratory for testing beyond standard model physics, dominantly coupling to the neutrino sector. We have provided one example for the case of weakly interacting particles that are emitted and then decay outside of the supernova, where we have shown that the non-observation of the neutrinos from this decay can provide bounds stronger by 1 order of magnitude compared to the cooling bounds that are the historical way. But really what I wanted to stress here is the opposite case of a strong secret interaction in the neutrino sector. What we have shown is that there is no observable that is affected by large changes due to the secret interaction nature. This is in some sense a very exciting conclusion because it is really a challenge for the future. It is still of great interest to try to understand what is the phenomenology of a supernova in the presence of secret interactions and whether a next galactic supernova will be able to constrain these secret interactions. The framework within which people have worked up until now is to try to see if some observable could be largely affected. We have shown that this is not the case. This only makes it more challenging and exciting for the future. It means that we should actually try to we should really take the mindset of precision physics and try to understand if these order unity changes are able by themselves to constrain new physics and possibly be disentangled from the relatively large uncertainty that we have from supernova theory modeling. So this is mostly what I want to say. So thanks a lot for your attention.
Thank you very much. This has been an absolutely fascinating talk. I'm realizing I have absolutely no intuition for hydrodynamics, especially relativistic hydrodynamics. But yeah, so this was very interesting to listen to. Do we have any questions? And while we're waiting for people to raise their hand if they have questions, I'll maybe start with one. You say there are only order of unity changes to observables. Does that apply to flavor observables as well? Or would
That's a
these
very
interactions change the relation between neutrino flavors?
Now, that's a very good question. So there is one very robust observables if we think about it. If we have the different coupling, sorry, I have not talked about flavor structure, but if we have the coupling to different flavors that are not too hierarchical, so in other words, they are not different by orders of magnitude, then that means that the different flavors should thermalize with one another, and so we should expect equipartition. So this is a very robust conclusion in a sense. It means that unless we fine-tune the coupling, for example, if we have only electron-neutrino interacting and the other not, unless we fine-tune the coupling, we should expect equipartition from the next galactic supernova. So if we do not observe it, this could rule out directly some of the models because it's very robust and simple observable. So flavor in itself provides some guidance, but it depends a lot on how you tune the flavor structure of the coupling. It's not, it's model dependent, I would say, but it does provide some information.
Okay, that makes sense. Thank you. Now, do we have any questions? Yes, Jim.
Very nice talk, Damiano. There's many interesting things we could talk about. So you're looking mostly at the cooling of the polar neutron star. I'm curious whether you think that there may be any changes to the actual formation of the polar neutron star during the collapse phase, due to the presence of secret interactions between the neutrinos, preventing their earlier escape during the collapse phase. Any thoughts about how that may change?
So we have not discussed much the accretion phase, and actually I think it's a very interesting question. I guess the reason we did not discuss much the accretion phase was that, okay, we always have in mind, can we do something with Supernova 1987A? And because of the sparsity of data, looking specifically at accretion phase was probably too difficult. But for next galactic supernova, this actually would be an interesting question. I have no good intuition whether the secret interaction could provide, because really the secret interactions typically are not able to trap the neutrinos because it's an interaction between one another. So the bulk velocity with which they escape is typically not so different. So similarly to the cooling phase, as I've shown for the cooling phase actually before, let me go here. Even though somewhat counterintuitive maybe, but the rate of outflow from a body into a vacuum, for example, is not changed by the secret interaction. So I would not expect that they would dramatically change the rate with which neutrinos are emitted from the surface of the neutron star, even in the accretion phase. But I have to say we have not looked at this in detail. So I think it's a very interesting question to which I do not have a more detailed answer at the moment.
Do we have any more questions?
So did I interpret what you just said earlier, that the self interactions would equipartition the neutrino flavors, right? So would that then stomp on the signatures that we're hoping to get from, say, mass hierarchy, where we would see a great difference between NUI and NUI power, for example?
So I mean, my intuitive understanding is that if these secret interactions again are not too hierarchical, then they simplify the problem rather than make it complex, because since they induce equipartition between all flavors, then at that point MSW effects, Mother effects would not be relevant, because they wouldn't. You cannot induce conversion between something that is already equal to one another. So I think that the secret interactions actually quite simplify the problem, because they tend to thermalize and equalize things. So in this respect, if it's a different question whether if we have hierarchical couplings, for example, if we couple only to NUI, they would definitely change things, because at that point you would have a different refractive index, let's say, for different flavors. So the Mother effect, I guess they would be changed in that case. But that depends again on the flavor structure of the coupling.
Okay. So when we finally see a supernova and we have no idea what the resulting signal means, we'll have to dig into things like this. Yeah. Okay.
Well, yeah. My impression is that we can only make, at the moment, I mean, at this stage of understanding, we can only we can only make very broad statements. So for example, we see an exgalactic supernova and we do not observe equipartition of flavors, then we can say that similar coupling of secret interactions can be excluded quite easily, because you should expect in a robust way equipartition. So this kind of broad features are easy to predict. More subtle features, of course, have a strong interplay with the uncertainty of supernova physics by themselves. And this refers not only to flavor, but it refers also to the, I did not mention this, but it refers also, for example, to the differences in the energy spectrum. If we did observe an exgalactic supernova, how can we say whether we are looking at the black or the blue curve, right? It's we don't know what to expect. So I don't think the main problem here is statistics. It's really theory related. It's more like a question of trying to disentangle this from the theory uncertainty, and it always requires some, it's always a challenge, I would say.
Yeah. This particular plot different models can mush it around a lot, but that's a real smoking gun if there's equipartition, and we don't expect that. So.
Yeah, exactly.
Yeah, thanks.
Just an experimental question more. Do you think that with the means that we have today, so S cube and Super Grande, and of course supernova explodes sooner and closer to us, can we actually detect this feature that we need to distinguish the existence of not of this secret interaction?
Yeah, I mean, as
we need more powerful detection scheme.
Yeah, I don't think really the detector would be the bottleneck of this problem. I really think that what is if we do have an exgalactic supernova, I would say this kind of differences are definitely something that we could detect. The main problem is not so much on the detection side, it's on the theory side. Like how can we disentangle, as we were mentioning now, how can we disentangle these from different model predictions for the neutrino spectrum? I think that's really the question. Like if we have of course, with supernova 1987A, we could not even do it with the statistics of the time. But with the next detectors, I think we do have enough statistics to distinguishing these features. The point is really how to disentangle them from the uncertainty. I think that's the main question and the main challenge that remains open at this stage.
Okay. If there are no further questions.
So Damiano, sorry, I would just add a couple of thoughts about what you just said. If you go and it goes back to what I said before, which is there is a very distinct feature that we expect in the neutrino emission, which is the neutronization burst, which in standard models is only electron neutrinos. But secret interactions would change that, right? They would produce a burst in mu and tau flavor as well. I know flavor oscillations will convert some of that, but and so it's a bit hard. Maybe flavor oscillations would wipe that out, make it harder to see. But I'll have to think about that particular idea.
I mean, I guess so, because when you have the neutronization burst, like collective flavor oscillation probably would not happen. So you would only have like matter effects, right? And that would be the main source of uncertainty, I guess. Again, like the conclusion in the presence of secret interactions tend to always be simpler than in the absence, because they simplify dynamics a lot. So the conclusion, even in that case, you should expect equipartition unless you assume very fine-tuned complex structure, even for the neutronization burst. Because they would. No, actually, no, I said something stupid. No, it's not true. For neutronization burst, no, because you would have to have neutrino, anti-neutrino, annihilating it. You don't have the anti-neutrinos. So actually, no, in that case, you would not expect a flavor difference, I guess. But I need to think about this more. So.
Well, I think you would definitely get ratio of neutral current to charged current events, which would differ than any oscillation scenario could predict with current values for the mixing parameters.
It depends on these, okay, because, I mean, it depends on whether the secret interactions are able to change the flavor. Like if you only have neutrinos. If you only have electron neutrinos, like you cannot produce other flavors, I think. You need also the anti-neutrinos. That's what I was saying.
Oh, okay.
If you want to change the flavor structure, you also need the anti-neutrinos to go to something else.
I see.